I'm including this in intra-seasonal variability, even though it's not precisely intra-seasonal variability, but it projects onto intra-seasonal variability. It's a story that's titled Monsoon South Asian Monsoon Predictability Beyond the Toga Legacy. Wow. During Toga, Tropical Ocean Global Atmosphere program that ran from the late 90s into the late 80s into the 90s, and then continues, of course, with the array in the Pacific. And it focused on El Nino observations, theories, modeling, predictions, and all the teleconnections like the Indian monsoon. For the longest time, Indian monsoon has always relied on its correlation with El Nino for predictions, and since El Nino can be predicted months in advance, it's often used to say whether monsoon can expect a drought or a flood. But we can start with this diagram, which shows the long-term average and the deviations with El Ninos and La Ninas being shown here with blue and red dots respectively. And the main message, of course, we have heard several times, is that only about 50% or less of the wet and dry years tend to be explained by La Nina and El Nino respectively. So there are non-El Nino predictors in the system, and we talked about the Atlantic Nino being one of the non-El Nino predictors. This paper here also shows the correlations between El Nino and the monsoon and how it has changed decadally, and sometimes that depends on the product you are using. So basically it's gone from being significant in some decades to non-significant in some decades, maybe non-significant again, but maybe recovering, and there is the lead lag months between the monsoon and El Nino. And the idea is that even when monsoon leads, you get some correlation which indicates that monsoon and El Nino are interactive systems. So El Nino has impact on the monsoon, and monsoon has a feedback on the El Nino. So that's not anything new. What is new in this paper is a focus on the North Atlantic and the argument that the Atlantic multi-decadal oscillation, as the name indicates, it's multi-decadal mode. As you know, the Atlantic has the North Atlantic oscillation between the Icelandic low and the Azores high, and mid-latitudes are of course full of waves. The main new idea here is that, which is building on some of the previous work, is that there is a way to create SSC surface temperature forced barotropic vorticity in the atmosphere, which is unusual for mid-latitudes where temperatures are colder. From the low latitudes, this is showing the relation between El Nino index and the upper level geopotential height anomalies, and you can see that the El Nino time period heating and shifts in heating create wave trains known typically as the Pacific North Atlantic Oscillation, originating in the West Pacific, going into the West Tropical Pacific, going into the Northeast mid-latitude Pacific, crossing over the US into the Atlantic in a great arc. So that is shown here, and it has all kinds of predictability consequences for the US, for example, because these waves take time to get over. And the argument here is that using multi-decadal Atlantic multi-decadal oscillation time series regressed against June, July, August, September temperatures and geopotential heights at the upper level. It's argued that there are ways in which sea surface temperatures in mid-latitudes can generate a barotropic vorticity response. It has to be barotropic because you want to lift the surface forcing to the upper atmosphere. Then the upper atmosphere can send a wave, and then you argue that the wave can reach India and create upper level cyclonic anticyclonic anomalies, which then at intraseasonal timescales create lower level cyclonic anticyclonic anomalies and produce monsoon interannual variability. So active break periods phase locked in each season add up to producing deficient or excess years in rainfall in an interannual sense. That's the variability that El Nino tries to predict as well. So lots of nice analysis. Okay, here is the caption that goes with this as well. Contrast between North Atlantic Indian monsoon and the Pacific North American teleconnection pattern. So this is a new terminology they are coining here called North Atlantic Indian teleconnection. So you are going from there down into the Indian region here. Spatial pattern of geopotential height associated with AMO that we just looked at. Regression of JJAS AMO multi-decadal mode on both JJAS SST in shading and deviation of JJAS 200 hectopascal geopotential height from zonal mean. So that's the Rossby wave pattern again. And in B, we looked at spatial pattern of geopotential height associated with ENSO corresponding to the PNA pattern. Regression of DJF Nino 3.4 SST on DJF 200 hectopascal geopotential height as viewed from the northern hemisphere. And in C, we are looking at Rossby wave train associated with the Atlantic multidecadal oscillation multidecadal mode, AMO multidecadal mode. Regression of JJS AMO multidecadal mode on JJS SST. Deviations on JJS 200 hectopascal wind vectors and 200 hectopascal geopotential height from the zonal mean, where the blue curves represent negative contours, red curves positive contours, and black curve represent the zero contour. So it's analyzed over 1850 to 2015, and the main idea is that even in the mid-latitude there is some indication that synoptic timescale or weather timescale variability tends to have a vertical structure that is baroclinic, whereas the intraseasonal timescale you can get barotropic structures. And then you look for correlations and additional causal inferences, because just correlations are obviously not always indicative of causality. But the main story I would say is that we still don't know the exact mechanism, so statistical approaches are used to argue that associated with sea surface temperatures there are barotropic vorticity responses in the mid-latitude over the North Atlantic, and there is kind of an SST gradient associated with that, and it's argued in a very hand-wavy sense that the SST gradient relates the mechanism of SST and barotropic vorticity to a mechanism that acts through the North Atlantic oscillation, which is again the Icelandic low and the Azores high. So kind of statistical inference based on this kind of mapping, and then additional details are provided like this. Let's read the caption and come back. Causal links between the ISMR, which is the Indian summer monsoon rainfall, and AMO in the presence of other potential drivers using PCMCI plus causal inference algorithm. Basically, nonlinear causal inferences go beyond correlations, try to remove effects of autoregression and so on to actually give you causal inferences, which is what is being tried here. In A here, we'll come back and look at causal links between the ISMR and the AMO. So, and North Atlantic SST, El Nino, NAO, PDO, Atlantic Nino, which is in the tropics, and the Indian Ocean dipole on seasonal timescales based on monthly anomalies of the indices for May, June, July, August, September, October, which is the MJO season in fact, during the period 1871 to 2017, obtained using multivariate causal framework at 95% alpha level. That's the confidence level. Monthly anomalies of SST are computed using this method. So without going into that, you can see here there are contemporaneous or simultaneous links, for example from NAO to AMO here, and there are lagged links from AMO into the monsoon region, and of course there's a direct contemporaneous link from El Nino to the monsoon as well, as we already know. And there are conflicting contemporaneous adjacencies here between the Indian Ocean dipole and Nino, because this peaks in September, October, November. It's always been an argument about whether this is really independent of El Nino or relates to El Nino through this maritime continent rainfall signal and this Indo-Pacific tripole and so on. So there are also unoriented contemporaneous adjacencies, so they can go either way. Similarly here, Atlantic Nino and AMO. There is a separate set of literature that looks at Atlantic Nino forcing off the monsoon as well, which is also argued to be non-ENSO predictability, even though Goswami this paper focuses on this link here. So AMO and PDO are linked with lags, and there is unoriented contemporaneous adjacency between AMO and Nino as well, and there is lagged feedback from the monsoon to the Nino, as we already mentioned, and it's also argued that IOD can influence Nino and Nino predictability and so on. So this is the way the color codes correspond to auto MCI modes and cross MCI arrows. This is a way of extracting causalities, for example, of the Atlantic meridional oscillation, Atlantic multi-decadal oscillation on the Indian monsoon, independent of El Nino. And the main argument here is that the Atlantic multi-decadal oscillation provides independent predictable signal predictability of the monsoon, and this is what is referred to as something beyond the Toga legacy. And here you can see the relations being implied again. North Atlantic SST anomaly generating barotropic vorticity signal acting through the NAO. And you can see here the caption: the seasonal link between North Atlantic SST and Indian summer monsoon rainfall is a result of causal links between NASST, North Atlantic oscillation, barotropic vorticity, Indian upper level vorticity IUV, Indian lower level vorticity ILV on intraseasonal timescales with daily intraseasonal filtered anomalies of indices using a 7-day moving average. So we are looking at interannual variability and predictability, but the process occurs at active break periods like the late season droughts and floods, for example, which is a separate paper that that is related to this mechanism. The indices for the JJS season from 1980 to 2010 are detrended, and so these are the details on how the analysis happens, which I won't go into. So if you believe now, based on this statistical analysis, causal inference analysis, and so on, that mid-latitude SST anomalies can generate barotropic vorticity and take the sea surface forcing to the upper level, then it's easy enough to perturb the zonal winds and generate waves which can go and perturb the Indian Ocean upper level vorticity, which projects onto the Indian Ocean Indian region lower level vorticity. So now you're talking about forcing of the ISMR, and pretty much anything you do to ISMR tends to act on active and break periods, and active break period variations tend to produce interannual anomalies. So that's the kind of the link we are talking about. Finally, looking at causal links between ISMR and AMO in the presence of other potential drivers using Granger causal inference algorithm. So another approach of going beyond correlations and eliminating autoregression kind of issues. Similar to figure 3a, but the causal inference links are obtained from monthly anomalies instead of the weekly anomalies of the same indices using linear Granger causality and nonlinear Granger causality framework at 95% significance level. There are details of arguments made as to how these things relate to each other. So you have AMO lagged correlation with the monsoon, NAO being part of that story, as we talked about in terms of SST anomaly acting through the gradient and the NAO, and the AMO has a link with lag to PDO, and then you have El Nino also a lagged relation with El Nino. Remembering, of course, that El Nino peaks in December, January, February. This peaks in June, July, August, and this can feed back to El Nino as well. And there are, of course, Atlantic Nino and IODs, which don't play here in terms of the links. Okay, so should I say something more? Just to make sure the numbers are mentioned, as in MCI Plus, both the linear and nonlinear causalities are shown as arrows with strength of association represented by arrow color, positive for red and negative for blue. So it's negative feedback, positive Nino creates deficits and vice versa, and so on. So positive barotropic vorticity, anticyclonic to cyclonic, and so you have to remember that the upper level vorticity is one direction, lower level will be the other direction. So there is that you have to remember carefully. Okay, so that's what is being argued here of this versus this. Okay, while node color represents the node autocorrelations, curved lines represent a time-lagged causal relation, and numbers denote lag in months. So here we are talking about lag in months, 2 to 1, 1 month here, 3 months. So this is a linear Granger causality, non-linear Granger causality. So just try to remember the main message. B.N. Goswami is the main senior author on this paper, and he's been pushing the idea of North Atlantic forcing of monsoons, and it has generally been at decadal time scale monsoon variability, but here we are talking about interannual variability of the monsoon acting through active break periods or intra-seasonal mechanisms. And the main crux of the finding here, as argued, is that sea surface temperature anomalies typically are forced by the atmosphere in the mid-latitude, but there are times when sea surface temperature anomalies are argued to produce barotropic vorticity response in the atmosphere and set off Rossby waves, which can take the signal from the North Atlantic into the monsoon domain. And there are other papers which relate the pathways of these Rossby waves, instead of being straight eastward to being southeastward, based on some other pressure patterns, Eurasian pressure pattern and so on, that have to form. Okay, you can follow up those details elsewhere. Okay.